Hi, in this lecture video, I will be discussing addition reaction of alkynes, and then we will focus on the catalytic hydrogenation reaction of the alkynes as the first types of reactions. So we see that alkyne undergo addition reaction very similar to the reactions of alkenes. And so these are the addition reaction right here. And the addition reaction of alkene are usually exothermic, meaning they produce heat. And the reason why they produce heat is as follows. In the course of this addition reaction right here, then the alkyne are then first converted into the alkene. And this alkene right here can further undergo addition reaction to be converted into the alkane. So overall, we refer to this as reductions of alkynes. But then there are types of addition reaction of alkyne. So both the name addition and reduction of alkyne would be appropriate. So let's see why that this reaction right here are exothermic. So if we think in terms of bond energy, in the case that the double bond is now converted into the triple bond is converted into a double bond, then we would then see that we are breaking one of this double bond right here, a pi bond. And when we look at the product that being produced over here, we are forming two sigma bond in here. And we all know already that sigma bond in general have higher bond energy compared to the pi bonds. So when we produce this sigma bond right here, energy are being released, and we're releasing a huge amount of energy compared to the energy that we put in to break this pi bond, which is normally less. So in the end, the reductions or the addition going from the alkyne to the alkene would then release energy or are said to be exothermic. And similarly, when we convert from a double bond into the single bond, then these are also exothermic as well. And again, because we are breaking a weak energy bond, this pi bond right here, but we making the high energy bond, the sigma bond. And so that's the reason why that addition reaction of alkene and alkyne are normally exothermic. So let's see now why that we also refer to this as a reduction reaction. So the reason why we call this reduction is because in the course of this reaction right here, then electrons are actually being added to this carbon-carbon triple bond right here. And we can imagine the following. If we were to break this pi bond right here, then now one electron will go to this carbon and one would then go to this carbon right here. And when we now undergo this addition reaction right here, and now when we react with AB, then we can see here that this carbon is going from one electron here on each of this carbon to now having two electrons in this carbon right here. So in the course of this reaction right here, the carbon that make up this triple bond right here are gaining electrons, and gaining electron are reduction. So this is why as we go from triple bond to a double bond, it is an addition reaction, but it is also a reduction reaction as well. And similarly, as we go from the double bond to the single bond, this is also a reduction reaction as well, or an addition reaction. So both of these names can be used. And now let's focus on the first one, the catalytic hydrogenation reaction of alkynes. So alkynes can actually be reduced to alkane by undergoing hydrogenation. So in which then we will have two molecules of hydrogen that be added across the triple bond to form the corresponding alkanes. And so this and these are the type of reaction that we have seen with alkene already. Alkene undergo very similar catalytic hydrogenation reaction. So in this case right here, with the alkyne, the triple bond, we can do the same thing. And we would need to use a catalyst, a metal catalyst, such as palladium, platinum, nickel, and so in the presence of hydrogen. And so basically, please note that the alkyne will be completely reduced, meaning reduced all the way to the alkane, in which the alkene intermediate cannot be stopped or isolated. So in the course of this reaction right here, when we take an alkyne, reacting this with hydrogen gas in the presence of a metal catalyst, we will be able to reduce this all the way to the alkane. Now, it has been found that it is possible for us to actually stop at the alkene, because the alkene would be the intermediate in between, that in this case right here we were not able to stop. But the question is, as a synthetic tool, if we want to synthesize the alkene from the alkyne, but not all the way to the alkane, so the question is it feasible that we can stop at the alkene without reducing all the way to the alkane? And the answer is yes. So through a lot of research, we have actually discovered that a catalyst that will allow us to do this. And this is known as the linear catalyst. So this linear catalyst right here, it is basically less reactive than the matter that we have seen above here. And we call this the deactivated or the poison catalyst because they are less reactive. And because now this matter right here are reactive, it is then possible for us to stop as the alkene. So how we will perform this reaction would then be as follows. Hydrogen in the presence of palladium and barium sulfate. And so basically, and also we have this quinoline as well and methanol. So all of these are being combined together. And this is then known as the linear catalyst. So if we were to take the alkyne, add hydrogen in the presence of this linear catalyst right here, then we'll be able to convert this alkyne right here into the alkene. But please note that the following, we will be able to make the cis alkene. And the reason why is because, again, the two hydrogen would then be added to the same side of this triple bond. And therefore, that pushes this group up and this group up. So in the end, the two R groups would then be ended on the same side. And the two hydrogen are then added to the same side. So basically, a cis alkene. And we'll be able to make that. And again, this will not get reduced further to the alkene, but we'll be able to stop at this cis alkene right here. So that would be the stereochemistry control in this reduction of alkene right here using linear catalyst. And now let's try some of this example right here. So if we were to now take this alkyne right here and treat this with H2 followed by linear catalyst, then what would be the products? And again, we recognize that this linear catalyst right here, it is a deactivated catalyst. So we'll be able to stop at the alkene. So here in this case right here, we'll be able to stop at the cis alkene. So we will have the methyl group there, and the isopropyl will be added on the same side, and now the two hydrogen are then added to the same side. So that will be the product right there in case that we do hydrogenation using linear catalyst. If we were to do hydrogenation using platinum as the catalyst, then again, this is so reactive that it will reduce all the way to the alkene. So the product that we're making right here will then be an alkane. So that will be the product right there with the second set of reagent. So quite easy.